All right, we're going to be taking a look at topic 4.9 on oxidation reduction reactions. This is part 1, and we are going to focus on what are called oxidation numbers. So, an important idea to help recognize oxidation reduction reactions is to identify the oxidation number or oxidation state of an atom. So before, we were just looking for certain types of reactions when we were looking for redox reactions. We were saying, okay, well, they have to be combustion, or they could be like single replacement. Those are always going to be redox reactions, or sometimes are single or double, synthesis or decomposition reactions. So we were looking for something that's an element and it's changing a charge. Well, now we're going to assign a charge to everything, so it gets a little bit easier to figure out if something's a redox reaction, okay? So atoms in ionic compounds have charges, and these are also their oxidation numbers. So when you have an ionic compound, we've already assigned most of our ions, our elements, charges. So that's convenient. But atoms in molecular compounds or in polyatomic ions can also have oxidation numbers or charges, although they don't have a real charge. So we call it an apparent charge or an assigned charge. So their oxidation numbers are assigned to charges so that we, as chemists, can figure out which atoms have the electrons in a reaction. Oxidation numbers are typically written as +1 or +2 or -1, -2. Instead of, when we write charges, usually write the number and then the charge, as we see up here with some of the charges like 2-, that kind of thing. So we write the number first, or the positive or negative first, and the number. Now, if you mix that up, it's not the end of the world on the AP exam. So we need to be able to assign everything a charge, is basically the moral of the story here. Everything needs to get a charge. And the way these rules work that we're going to look at is basically in molecular compounds where we don't have charges already. The more electronegative the atom is, the more it's going to have the electrons, so the more negative it'll be. So that's something you kind of keep in mind. Your more electronegative atoms are going to be more negative. So we have some rules for finding or assigning oxidation numbers. So these are the rules we're going to live by. As we work through these, we're going to start to get used to some of these basic rules and be able to figure out our oxidation numbers. So let's start with easy one. Oxidation number for elements is 0, and this includes diatomic elements. So as we look at the examples up here, or the rules up here, we're going to look at examples down below that go with that. So if something's written just as its element, there's no charge written, there's nothing with it, its oxidation number is going to be 0. Okay, so something in its elemental form would be something like hydrogen here. So the way we write oxidation numbers is we just list our elements that are in the chemical and then write their oxidation number. I write my zeros with a line through it just to make it very clear that that's a 0. Something else in its elemental form, this has a charge already, so we're going to ignore that. The iron here is in its elemental form. There's no other chemical with it. It's telling us it's a solid, so a lot of times our solids like that, especially our metals, will have that, and we'll be able to know it's in its elemental form. So it will also have an oxidation number of 0. All right, we don't have any others. You could always pause as we do these and look for more examples down below in your practice of things like this one, like each rule, okay? So if we look at our next rule, it says the oxidation number for ions is their charge. So let's see if we have any ions here. If we want to recognize an ion, we need a charge to it. Well, here is calcium with its charge. So calcium's oxidation number would be equal to its charge, so +2. Okay. When we look at, let's find an ionic compound, just a simple one with 2 elements, like iron chloride. The oxidation number for those ions would be equal to their charge. So we've got iron and chlorine. I know chlorine's charge is always -1, so I'm going to go ahead and put that. Iron, we'd base it off the charge of the ionic compound. There's 3 chlorines, so that'd be -3 total in the compound. And so iron would have to be +3 to balance that. So when we list these, we want it for the individual atoms. So each of these 3 chlorines has a negative charge. We don't want the total charge here, the total charge. Okay? All right, let's see if we find any more ionic compounds. We have some, but they have polyatomic ions, so we're going to skip those for now. MnO2 is just 2 ions, so those would follow their normal charge. So we've got manganese and we've got oxygen. Oxygen's normal charge in an ionic compound is -2. And there's 2 of those, so it's a total of -4. So manganese would have to be +4. Okay. So that takes care of a good chunk of our substances with just the first 2 rules here. Now it says for number 3, the oxidation number for oxygen in a compound is -2. Okay, well this can start helping with things like our covalent compounds like water here. So let's go ahead and write hydrogen and oxygen. We're going to give the oxygen, even though it's a covalent compound and they don't have no charges normally, we're going to assign oxygen as -2. And number 4 can help us with hydrogen. Hydrogen in a compound is +1. So we're going to assign hydrogen as +1. Okay. And then other than that, when we have a compound like this, I'm going to jump to number 6 here. It says all oxidation numbers add up to the overall charge of the compound or polyatomic ion. All right, so the overall charge of water, it doesn't have a charge. It's 0. Okay, there's no charge written there. So these should add up to 0. Well, we have 2 hydrogens that are each +1, plus oxygen that is a -2. So that does add up to 0. So we check out here. Okay, this one works. So you can always check it that way to make sure it's adding up to 0. All right, let's check another one that has oxygen or hydrogen, but no polyatomics. These all have polyatomic ions. We'll come back to those. Let's check out C2H6. C and H. Okay, not an ionic compound, so we got to assign its charges. Well, we'll start with something that has a rule. Hydrogen has a rule. It says it's going to be +1. And I got to figure out what carbon's going to be. Okay, well, we can use a little formula like I did here. When I add these together, they need to add up to 0. Okay, I've got hydrogen that's +1, and there's 6 of them. And I've got 2 carbons, and I need to know what its oxidation number is going to be. Well, that means I have 2x plus 6 equals 0. Okay, well, if I keep working this out, I'm going to get, let's see, I can subtract the 6 to the other side, so I get 2x equals -6. So my x, if I divide by 2, is -3. So that means each of my carbons needs to be -3. And we can always check it. -3 times 2 gives me -6, plus 6 gives me 0. So those are my oxidation numbers for that. So this is how we can use this rule here, that the overall has to add up to the overall charge of the compound to help us find some of them we don't have a rule for. So I knew hydrogen and I calculated carbon based off of that. Now all these other ones have some sort of polyatomic ion in them. Let's start with this one. This one is a polyatomic ion. So we've got hydrogen, sulfur, and oxygen. Now we have a rule for oxygen. It says it's -2. And we have a rule for hydrogen saying it's +1. So we need to calculate what's going on here to figure out sulfur. Okay, so I'm going to do a little calculation. I feel like I'm going to run out of space, but we'll do it here. Okay, so we don't know. Actually, I'm going to do it over here so I have space, all right? So we've got hydrogen, which is +1, and we only have 1 of them. Plus we have a mystery sulfur. Plus we have 3 oxygens that are each -2. And the whole thing needs to add up to the charge that's given. This is a -1 charge on this chemical. on this ion. So all of this needs to add up to -1. So we can do a little math here. I got 1 plus x minus 6 equals -1. So 1 and -6 would give me -5 equals -1. If I add 5 to the other side, -1 plus 5 is 4. So my x is equal to 4. My sulfur is equal to positive 4. So we can always test that out. 1 plus 4 gives me 5, plus -6 is -1. So we can do a little side calculation to help us figure out the one we're missing. Okay? We can do that for any chemical that we're not sure of one of our elements in. Okay, let's check out this one that has a polyatomic ion. So NH4 and Cl. Okay, well, Cl is always negative. This NH4 part is always positive. So we're going to need nitrogen, hydrogen, and chlorine. Chlorine is negative. It's going to keep its regular charge. Hydrogen has a rule that says it's +1. So we need to calculate what nitrogen is going to be. Okay, again, I'm going to do a little side calculation. I'm going to run out of space. Let me use a sticky note. So let's do it this way. So we've got nitrogen that we don't know, and there's only one of them, plus 4 hydrogens that are +1, plus 1 chlorine that's -1, and that's going to all total up to the charge on the whole thing, which was 0. So we've got x plus 4 minus 1 is 0, so x plus 3 is 0. So we subtract 3 from each side, and we get x equals -3. So our nitrogen is what we were missing, so it's -3. And we can always check it. If I put -3 plus 4 minus 1 would give us 0. That's true. All right. So that's how we can approach these different chemicals. I'll show you another strategy that can help as well. So if we had this one, KMNO4, so if I just look at the ions, I know potassium is +1 because that's its normal charge. But this MnO4, that has to add up to a negative charge. Well, instead of looking at this entire thing, I can just look at the MnO4 part, and it needs to add up to -1. Okay, so we know oxygen is going to be -2. That's one of our rules. So I don't know manganese. I have 4 oxygens that are each -2, and that polyatomic ion needs to add up to its charge. Okay, so we can simplify things and not have to include that potassium in there. Whatever works more for you. So we've got x minus 8 equals -1. So x equals, we add 8, we get 7. So manganese is a +7 for its oxidation number. All right, let's try another one. All right, we'll try this K2CrO4. So we've got potassium, chromium, and oxygen. We know oxygen's -2. Potassium's going to follow its normal charge, +1. Again, we can set up our little math problem for this. So I've got 2 potassium that are positive, plus I've got a chromium I don't know, plus 4 oxygens that are -2, and it has to add up to the charge of 0. All right, so we've got 2 plus x minus 8 equals 0. 2 and -8 is going to be -6. And we're going to add 6 to both sides, so x is 6. So chromium is going to be a +6. All right. We'll do one more, and then you can practice some of these. All right. Sodium carbonate. So sodium, carbon, and oxygen. Oxygen's got a rule is -2. Sodium's going to follow its normal ion charge, +1. We got to calculate carbon. And we can think about this. It's like carbon doesn't usually have a charge to it. So that's why we're having to calculate it. And we can see, actually we only have one thing with carbon. So we'll calculate this one. We'll compare it to some other ones. So we've got 2 sodium that are +1. We've got mystery carbon. 3 oxygens that are -2. So that's got to be equal to 0. So we've got 2 plus x minus 6 is 0. 2 and -6 is -4. So x equals +4. So our carbon is +4 here. So we can see, but comparing these two, carbon is drastically different between these two compounds. All right. In this one here, our most electronegative atom is oxygen, so it's going to get the most negative charge. We've got 3 oxygens kind of hogging all those electrons. So carbon's going to be more positive. But here, carbon's more electronegative than hydrogen, so it's going to be attracting the electrons more and ends up being negative. So that's how we get these different charges. Now, you notice oxygen is one of those that's always -2, and it's because that oxygen is one of our most electronegative atoms. We know it's going to be pulling those electrons towards it. Similar with our chlorine or any others on here. And then we got our metals, things like calcium and potassium and iron all being positive because those elements tend to be positive, right? They tend to have that positive charge. We got nitrogen here. That's a non-metal. It's more electronegative than hydrogen and chlorine, so it's going to be pulling the more electrons towards it. So that's how we're getting these charges. They've developed rules to give us a way to assign a charge to something so we can figure out what's going on with our chemicals. So we're kind of taking baby steps in it right now. We're going to practice assigning charges to chemicals, and then we're going to see how we apply those in a chemical reaction next. So try these practice questions out. If you get stuck on any, let me know. We can always go over them, and we'll go from there. Thanks, guys.